All right, good afternoon, good morning, good evening, good night, depending on when you're watching this video. So this video will be a walkthrough of the first summary exercise on binomial random variables. This is slide 26 of lecture set number 4. Okay, so in this illustration, we have a university claims that 80% of its basketball players get degrees. Suppose 20 players enter the basketball program. At the end of a 4-year term, calculate the following: the expected number of graduates with a standard deviation, the probability 11 players graduate, the probability at least 90% of players graduate, the probability at least 1 player graduates. All right, so we are going to assume for all problems that little n is equal to 20. So the number of players entering the program are going to be our sample size, or the number of trials that are taking place in this binomial experiment. The probability the individual player gets a degree is 0.8. Okay, so each player has an 80% chance of finishing, essentially. And we want to know across the 20 players, how many do we expect to graduate? And we want the standard deviation associated with that. So what is the expected number of graduates at the end of a 4-year term with standard deviation? All right, so each player either gets the degree or they do not. All right, so X counts number of players that get a degree. So this is a success or failure random variable. The player either gets the degree or they do not. And we are counting across 20 players. That's what makes this binomial. So the expected number of players, which we're going to call, okay, so we're going to have the expected number of, so the expected value of X is equal to mu of X. Okay. And this is equal to N times P, because X is binomial. So that's 20 times 0.8, which is 16. The standard deviation of X is equal to the square root of N times P, 1 minus P. Okay, so this is the square root of 20 times 0.8 times 0.2. Okay, and that is equal to the square root of 3.2, which is equal to 1.789. Okay. So this is our expected number of graduates, 16, plus or minus 1.789 players. All right, part B asks, what is the probability 11 players graduate? Okay, so we have the probability X is equal to X is N, choose X, P to the X, 1 minus P to the N minus X. So we have the probability X equals 11 is equal to 20, choose 11, 0.8 to the 11, 1 minus 0.8 to the 20 minus 11. Okay, so this is 20, choose 11, 0.8 to the 11, 0.2 to the 9. All right, this is 167,900 multiplied by 0.085899 multiplied by 0.123456512, which is equal to 0.007. All right, so therefore the probability exactly 11 players graduate with a degree is 0.7%. And that's an application of the binomial probability formula. All right, so we're going to look at two more examples illustrating this formula in two slightly different contexts. So part C says, what is the probability at least 90% of players graduate? Okay, so we want probability at least 90% of players graduate. Okay, we have 20 players entering the program. 90% of 20 is 18. So this is the probability X is greater than or equal to 18, right? So 20 players total in the program, 90% of the players would be 18. We want at least 90% graduating. So that's 90% or more. So we want to know the probability at least 18 players graduate. Okay, so this thing is going to be the probability X equals 18 plus the probability X equals 19 plus the probability X equals 20. Okay, so this is simply three applications of that formula. So we have 20 choose 18, 0.8 to the 18, 0.2 to the 2, plus 20 choose 19, 0.8 to the 19, 0.2 to the 1, plus 20 choose 20, which is 0.8 to the 20, 0.2 to the 0. All right, so this is going to give us 0.1369 plus 0.0576 plus 0.0115. Okay. All right, and that gives us 0.206. Oh, that should be fine. I'm just going to make sure I didn't make a mistake here. Yes. 0.206. All right. And then in part D, it asks, what is the probability at least one player graduates? So the probability X is greater than or equal to 1. Okay, so there's a hard way to do this, which would be we take X equals 1 plus X equals 2 plus X equals 3 plus all the way up to X equals 20. So we add all of the probabilities in that space together. Or since P X equals 0 is not included, the probability X is greater than or equal to 1 is equal to 1 minus the probability X equals 0. This is 1 minus 20 choose 0, 0.8 to the 0, 0.2 to the 20. This is 1 minus 0. Okay, so this is 1 minus 1.049 times 10 to the negative 14. So this is approximately equal to 1.000. Okay, so the probability at least one student graduates is essentially 100%. Okay. Oh, sorry. And I forgot to do a little statement above. So the probability at least 90% of students graduate is 20.6%. And the probability at least one student graduates is approximately 100%. Okay, so four total problems, three illustrations of using the binomial probability formula in different contexts. And the first problem illustrated computation of the mean and the standard deviation when the discrete random variable is binomial. So remember that in order to use these formula, we must first identify the problem as being a binomial probability problem. So we have to identify the random variable x as being a binomial random variable. As always, if you have any questions, please let me know.